Lesson 4, many body problems. Hey, what if we have more than one mass attached with a rope? Like this. We can do this really complicatedly, or we can be clever. And we're going to be clever. First of all, I'm going to tell you that if we're using a rope, I will never be doing this. I'm not going to be giving the rope a big jerk. The pulls are always going to be smooth, and what that means is I can always assume that both masses, this one and this one, are accelerating at the same rate. Different direction, yes, but the magnitude will be the same. I will be able to assume that they have the same A. And in fact, what that means is, what I'm usually going to do, if you give me more than one mass, I'm going to temporarily just pretend it's one big Ubermass. See a little bit of German there? One big Ubermass. I'll solve for the Uber acceleration, and then I'll go look at the masses individually. Easy to explain, even easier to do. So in these problems, in many body problems, we have several objects connected together by strings. The easy approach is to realize that we can treat this system as a single object, since all parts are accelerating at the same rate. So example 1 says, find the acceleration and the string tensions. The solution is we're going to treat the system as a single object and write a force equation. I generally start on the left and work my way across. You don't have to. I just want all of my numbering to look the same. You can do whatever you want. But usually I'll start on the left and work my way across. So I'm going to start out looking at that 3 kilogram mass. Hey, what are they asking me to find here? Acceleration and tension. You know what this is a job for? Free body diagram. Oh, you know what though, Rob? I'm going to lie. Did they give me a nice picture this time? What I'm going to start to do now, rather than redraw everything representing the masses with a dot, if there's 2 masses attached by ropes, I tend to just label everything on the picture, because the ropes are in the picture, it helps me see how things are going to relate better. So although technically a free body diagram is representing the mass with a dot, I'm going to label my forces. What are the forces acting on this 3 kilogram mass? Get the obvious one, which is mg. Is there more than one mass, though, this time? Yeah. I'm going to call it m1g. I'll call the second mass m2. If there's a third mass, I'll call it. Yeah, okay. Makes sense. Is that mass sinking into the ground like quicksand? Is it flying into the like Superman? So there must be a force up. What force is that? Is there more than one mass on the surface here? Is there going to be more than one normal force because there's 2 different masses? I'll call this normal force number 1 to go with mass number 1. What else? Is there friction? No. How do you know? I snuck it in the diagram. What's mu? I don't know. What's mu with you? What's mu? 0. Okay. However, which way is this thing accelerating? So there must be a force pulling it to the right, and this is the key. It's not the 20. And the reason I know it's not the 20 is the 20 is not touching the 3 kilogram mass. What is touching the 3 kilogram mass? A rope. Devin, what have we traditionally called the force from? Was it you that said that? Tension. Okay. That's all of the forces on mass 1. What about the 2 kilogram mass, mass 2? What are the forces acting on it? Get the obvious one. Hopefully you're starting to find a bit of a rhythm and a cadence and a system to my approach. I strongly encourage you, go in the same order. I know many of you want to do the obscure forces first. Do them last. Get the obvious ones. So gravity. Oh, I'll call that M2G. Mr. Dueck, yes, Lewis. Shouldn't you have drawn M1G bigger and M2G smaller because M1 is heavier? I'm not going to be that fussy, but okay, if you did that, I'd be impressed. Is mass 2 sinking into the ground like quicksand? Is it flying into the air like Superman? Well then, there must be another force up the same size as M2G. I'll call that normal force number 2. What else? Oh! Here's the 20 newtons, the applied force. I'll put an arrow there. If you wanted to, you could even write F applied. Usually if I put an arrow next to the 20, that's enough for me to clue in that I better not forget the 20. Come in! Hang on one second. What else? And I heard somebody say tension. There is, and the reason there is a tension, this is a Newton's third law, forces come in pairs. The string is pulling this mass to the right, the string will be pulling this mass to the left. It's the same piece of string, and so it is the same tension. I defy you to try pulling on a rope with different strengths on different ends. It can't be done. The tension through a rope is always going to be the same. There is my, yeah? Have I got an arrow pointing there? Have I got an arrow pointing to the left? Hold that question, because I don't want to deal with negatives and positives. I'm going to deal with winners and losers. Okay? There's all my forces. Vertically, my forces are balanced. So now I'm going to write a horizontal force equation, and I'm going to walk down the entire rope. First of all, which way do you think this thing is accelerating? To the right, that's winner. Okay? Anything pointing to the right, now I'll answer your question, Tyler, is going to be a winner plus. Anything pointing to the left is going to be a loser minus. So my equation is going to look like this. 20, winner. Walk along the rope, walk around. I run into this tension. This tension here, loser or winner? Negative. This tension here, loser or winner? Positive. Are there any other forces along the rope? Equals. And here's the other twist that I make. Up until now, it's always been MA. Have we looked at forces from more than one mass in our going along the rope? Let me ask you again. Have we looked at forces from more than one mass, Rob? Yes. Well, then I better have more than one mass over here. That's the twist I have to make. Oh, I'm so relaxed. You know why I'm relaxed? Because I'm losing tension, baby. Right? Nice. Yes, I'll use that joke every time, but it's also a dumb way to remember it. What did they want me to find first? What was the I've scrolled down, but what does it say in the question? Find what? Read, please. What does it say in the question? Sorry. Oh, how would I get the A by itself? Divide by both masses. Divide by the bracket. Oh. See, after all that setup, we actually get a really nice equation. We're going to get A equals 20 divided by M1 plus M2. 20 divided by 3 plus 2. And I'm even going to argue this question is so nice that, Lewis, you don't need a calculator. You can do it in your head. What is 3 plus 2? What's 20 divided by 5? We get an acceleration of 4. Oh, to 2 sig figs, I'll go 4.0 meters per second squared. Is that okay? Oh, they wanted me to find something else. They said, find the acceleration and tension. To find tension, we look at one mass. Which one? Doesn't matter. You'll get the same answer no matter which mass you use, but often you're going to find one mass will be easier. Which mass will be easier? I like to use the mass where tension is the winner, where tension is pointing to the winning direction. What was the winning direction in this time? So in which mass is tension pointing to the right? Mass 1 or mass 2? Okay. Let's write an equation only for mass 1. Okay? Vertically, it's a tie. I'm ignoring all this. Just pretend it's gone in your mind. Pretend that's not there at all. I'll erase that in a second. Okay? What are the forces acting on mass 1? I got those on there already. There's my diagram. Who's winning? Look at mass 1. Who's winning? Tension. Who's losing? It's a trick question. No one. So if I write an equation for mass 1, I get this. Tension equals, did I say mass 1? Now I'm not going to put the mass of both. Now I'm going to put mass 1A. It's still winner minus loser equals MA. I'm adjusting the M as I need it. Do I know mass 1? How big? Do I know A? That's why I had to find the overall acceleration first. Because if the overall acceleration is 4, that means each individual one is also accelerating at 4. In fact, it's going to be 3 times 4. Your Grace, if you would deign us with your mind and solve that in your head, could you privilege us with a solution, your Lord? Sorry? 12 what? Ah, it's a force. Did you do it? What, Jordan? What if I decided to use mass 2? You'll get the same answer. It's going to have a few more forces. It's going to be a more complicated equation, which is why I wouldn't have used it. But you know what? For consistency, let's check the other mass. I'm going to go back up here to this diagram. So now I'm pretending that none of that exists. Vertically, it's a tie. What's the horizontal force equation for mass 2? Who's winning? 20. Who's losing? Tension. Okay, so if I was writing an equation for mass 2, it would look like this. 20 minus tension equals, did I say for mass 2? Then it's going to be mass 2A. So the key you have to recognize is when are you doing an equation for more than one mass? And it's pretty obvious because you've gone down the entire rope and you've taken forces from more than one mass. Then it's going to be the mass of everything times A. Or if you're looking at one mass, then it's just going to be that mass times A. How would I get the T by itself? I would plus it to this side, and at the same time, I would minus it to that side. I would get this. 20 minus M2A equals tension. Now, I'm hoping this will work out to 12, because that's what I found with the other mass. 20 minus, what was mass 2?
2.
And what was the acceleration?
4.
What is 20 take away 2 times 4? Is it also 20 take away? Aha! Yay, I know I'm right. But can you see, Quinn, the first mass, less work? One will always be less work, but doesn't matter. You get the same answer no matter what. What's our strategy going to be? You give me more than one mass, I'll start out by finding the overall acceleration, writing an equation, winner minus loser of everything equals the mass of everything times A. Then I'll go look at individual masses to find individual forces. Or, if you reverse it, what if you don't give me the overall acceleration, but you give me the tension? I can use the tension to find any individual masses to find the overall acceleration. When we have several masses connected by strings, we need to realize that the first string accelerates the first mass, but the second string accelerates both of the first two masses. In other words, how many strings do I have in this question? 2. I'm going to have 2 different tensions. I'll call it tension 1 and tension 2. I'll start over on the left-hand side again. What are the forces acting on this 3 kilogram mass? Get the obvious one. I'll call it M1G since there's more than one mass. Normal force number 1. Is there friction? By the way, can you see, it wouldn't be that tough for me to add friction. I just have one more loser force. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, M1G. Not that much harder to add it. It's more typing, but not, I would argue, much more difficult. What else? So no friction. Oh, but is it accelerating to the right? Ah, there's a rope. Ah! Tension 1. What are the forces acting on mass 2? Get the obvious one. M2G. Is it sinking into the ground like quicksand? Is it flying into the air like Superman? No, you say. Normal force number 2. Is there a rope on the left of it? Yes. Which way is the rope to the left of it applying a force? This is a forces come in pairs. Is there a rope on the right of it? Yeah, that's what's accelerating it forwards. I'll call that tension 2. What are the forces acting on this 5 kilogram mass? Get the obvious one. Gravity, you say. I'll call it M3G. What else? Normal force number 3. What else? Oh, here's my applied of 20. And tension 2 to the left. What do they want me to find? Okay, I'm going to treat this all as one big mass. I'm going to list all the forces along the rope. Because you can see vertically it's a tie, right, Carolyn? Yeah? With me? Yeah. Okay. So who's winning? Who's winning? If this is accelerating at all, which way must it be accelerating? Right's winning. This goes to your question again, Ty. Now, everything to the right is going to be positive. Anything pointing to the left is going to be negative. And this gets away from, do I want down be positive? Up? You know what? Whichever is the most convenient for me mathematically. Who's winning? The 20. So my equation is going to look like this. 20. And now I'm going to walk along the rope. I run into tension 2. Which way is the first tension? Which way is this tension 2 pointing? To the left? Loser. Oh, but I run into tension 2 again. Which way is it pointing? By the way, I just saw your little badge. Nice political statement there. And then I run into tension 1, which is a loser. And then I run into tension 1 again, pointing to the right. It's a winner. Is there friction in this question? Everybody say no. But would it be hard for me to add friction? No, I'd have a few more losers going because they'd all be pointing to the left. Okay. What does that equal? Have I included forces from more than one mass? Which masses? Mass 3, mass 2, and mass 1? You know what? I'm going to go like this. M all. That's A didn't want to write properly. Let's try that again. M all times A. Or you can write in brackets M1 plus M2 plus M3. I'm on a beach, sitting in the sand, by the ocean, reading a book, because there's no tension. Right? Mr. Dewick, will tension always cancel? Not if you're looking at individual masses. But if you're looking at the entire system, will it always cancel? I'm trying to think. This year, I think so. I can't say always in the greater physics scheme, but this year, I'm pretty sure. Yeah?
What's the situation in which it wouldn't?
I'm trying to think of one right now. Be patient. I'm not certain, and that's why I gave you so much hesitancy in that answer. That's why I said this year, I think so. Trying to think if there's one that it might not. But my brain right now with my pirate wig right now is not at its best. People on the internet are going, pirate wig? What the heck is this? It's Halloween, people! Okay. Oh. Hey, Rob, what did they want me to find? What was the first thing they asked me to find?
Acceleration.
Oh, how would I get the A by itself?
Divide by M.
Oh. I mean, I love the fact that this complicated beast ends up with really as simple an equation as we could hope for. Turns out the acceleration, oh, let's go in blue, Mr. Dewick, is going to be 20 divided by mass 1 plus mass 2 plus mass 3, the mass of all of them. 20 divided by 3 plus 2 plus 5. Hey, Stitch, what is 3 plus 2 plus 5? What's 20 divided by 10 in your head? And again, if they don't work out evenly, is there more than one number in the bottom? Put the bottom in brackets. It would be 20 divided by bracket 3 plus 2 plus 5. But this one, I cooked the numbers nicely. 20 what? It's an acceleration. Yep. Okay. What else did they want me to find? Okay. Let's find tension 1 first. I might be able to do it using mass 2 because tension 1 is on mass 2, but do I know tension 2? No, you know what? This would be a dumb one to pick. Let's pick mass 1. What are the forces? Oh, I'm not going to say draw a free body diagram. Who's winning mass 1? Tension 1. Who's losing? Trick question. No one. If I want to find the tension using mass 1, my equation is going to be tension 1 equals, and I said mass 1, so it's going to be mass 1 times A. Riley, how big was mass 1? Oh, and how big was the acceleration, which is why I had to do that first? Oh, good gosh. In your head, Riley, 3 times 2 is? 6 what? Tension. Newtons. Let's find tension 2. I could find tension 2 using mass 2 now that I know tension 1, but I'd be using tension 1 to do it. You know what? If I was clever, I would use mass 3 and the 20. I would use the stuff that they gave me. Now, if this was a test question and I finished the test early, then I would go back and I would find tension 2 using mass 2 and tension 1. And if I got the same answer, then I know all my tensions are right. Yay! But I would only do that if I had the time. So it says chord 2, and for some reason I wanted you to use mass 2. I'm going to say no. I'm going to do mass 3. What are the forces acting on mass? Oh, no, sorry. Mass 3. Who's winning? Mass 3. Who's winning? 20. Who's losing? Minus tension 2, and that equals mass 3 times A. Now, if you wanted to, you could have gone for mass 2, tension 2 is winning, minus tension 1 is losing, equals mass 2 times A. And you will get the same answer for both of these. You could argue this equation is a little easier to get tension 2 by itself because it's just plus it over. This equation is smarter on a test because it uses data that they gave me instead of data that I calculated. So I'm smarter on tests, and I can handle this equation here in one step. I like to move tension 2 over because it's negative, so I'll plus it, whilst at the same time, I'll minus the M3A over to this side. I'm going to get tension 2 equals 20 take away M3A equals 20 take away. Which mass did I use here? M3. How big is mass 3, Tyler? And what was A? I've forgotten. A. Can't be kilograms, I can tell you that right now. What was the acceleration? Turn back. Yeah, go. It's there. We got it somewhere, right? Oh, there. In your head, Tyler, what is 20 take away 5 times 2? What's 5 times 2? 10? Oh, did you say 10? By the way, technically, if I wanted to go to 2 sig figs, I'd have to put a decimal there, right? 10 what? It's a tension. Newtons. You can try, if you want to, later on your own, solving for tension that way. I guarantee you'll get 10 newtons. Hey, what if we have one hanging over a cliff? No problem. The pulley will transfer the force along the rope. We're still going to do all of the forces along the rope in one equation. And now this is going to start to let us get into some nice two-dimensional questions where stuff is moving left, right, and stuff is moving up, down. So if we have a hanging mass and no external force, we need to well, ready? It says identify the net force and then find the acceleration and chord tensions. By identifying the net force, what they're really saying is write a net force equation. Let's start with the 2. What are the forces acting on the 2? Get the obvious one. Is there more than one mass in this question? Well, then I'll call this M1G. What else? Is this mass sinking into the ground like quicksand? Is it flying into the air like Superman? And I'll call it normal force number 1 to go with mass number 1. Is there friction in this question? No. How do I know? What's mu? I don't know. What's mu with you? What's mu? 0. Okay? Again, though, we're going to add friction shortly, and you're going to see all it does is it makes the questions longer. But I can't really say it makes them that much tougher. It's more typing. Oh, is there a rope? You know what? Tension's pulling this guy to the right. Let's do the 4 kilogram mass. What are the forces acting on the 4 kilogram mass? Get the obvious one. Gravity. Is there more than one mass, Lewis? I'll call it M2G. There is more than one mass, so I'll call it M2G. What else? Is there a rope? Tension. Is this thing sitting on a surface, or is it hanging in midair? So is there a normal force? No, don't get normal force happy here. Every so often kids start sticking normal forces everywhere. No, you've got to be sitting on a surface. In fact, that's it. That's it. Now, who's winning? I'm telling you right now, first of all, imagine, since there's no friction, imagine that's ice. If you were standing on ice and someone was hanging over a cliff, are you moving that way at all? No. Who's winning then? Which one? There's two of them. Yes. So anything, now I'm going to follow stuff along the rope. Anything that ends up pointing down is going to be winner plus. Anything that when it gets over here in my imagination ends up pointing up is going to be loser minus. Okay? You know what? With the Donald Trump sticker, loser, classic Donald Trump saying, right? That's one of his things. I'm a winner. You're all losers, right? You've watched Donald. So, ready? Who's winning? Winner. Let's walk along the rope. This tension here, winner or loser? Loser. Keep walking. Now, I have to imagine this coming over here. This initially looks like it's to the right and it's a winner. Or, sorry, when it gets over here, which way does it end up pointing? Down. That's a winner. Am I going to include M1G? Is it along the rope? No, nothing else. This bugs some kids. What? Don't worry. If there was friction, then it would show up in the normal force. I don't know the normal force. Look. But since you're on ice, what does that equal? Have I taken forces from more than one mass? Well, then I better have RELAX. Why am I relaxed? Oh, I love it when I lose tension. So nice. Okay. If I stopped right here, this is the first part where it says identify the net force. There's my net force equation. Then find. Oh, how would I get the A by itself? You may start to notice this gets a little repetitive. I hope it is. Apparently, I'm going to divide by the masses. Yes? A is going to be, the M2G stays where it is. Four times 9.8 divided by 2 plus 4. Get your calculators out. You need to try typing this in because many of you will type this in wrong. Get your calculators out. You need to try typing this in because many of you will type this in wrong. Let's see if I can do this in my head, though. It's going to be 4 times 9.8 divided by 6. That's the same as 2 times 9.8 divided by 3. 2 times 9.8 is going to be 19.6 divided by 3 is going to be 6. 6.6? 6.5. It's the pirate wig. 6.5 even? Units. It's an acceleration. Okay. So, identify the net force. Check. Identify the acceleration. Check. What's the final thing they want me to find? Yeah. Now it says chord tensions. How many ropes are there in this question? Just one tension. I'm going to use the one where tension is a winner. Which mass is tension a winner? Mass 1 or mass 2? I'm going to do my equation for mass 1. So mass 1, I can fit it right. I think I can fit it right here, actually. Mass 1 is going to be, well, who's winning on mass 1? Tension. Who's losing on mass 1? Don't be talking M1G or F normal in the direction of the rope. Who's losing? It's a trick question. So it's going to be M1A. The tension is going to be 2 times 6.5, and I'm pretty sure that works out to an even 13 newtons. Now, if, Carolyn, you decided to use this, you would go M2G minus tension equals M2A. Trust me, when you got the tension by itself, you'd also get 13. Okay? Apparently, for some reason, I gave you more work here, but we crammed it all next to this. That works. For problems that involve friction, we can still use the system approach to find the acceleration. But the tension calculations are a little tricky. Actually, they're not. There are two ways to do these when there's friction. The first way is technically the nerdier way. You can figure out ahead of time how big each friction force is by going mu times the normal force. I don't know the normal force. Look, 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 look. And then by knowing how big the total friction is, you can figure out whether it's winning or losing. That's the nerdy way. The second way is the easy way. You guess who's winning. And you'll know you've guessed wrong if when you solve for acceleration, you get a negative answer. It means what you thought the winner was actually the... And you go back and you make every winner a loser and every loser a winner, which just means in your equation, you make any minus a plus and any plus a minus. You don't have to really rewrite the equation. You can fix it all even in pen and redo it. I do it that way because it's the laziest. And this is one of the few times when I don't give in to my inner nerd and figure it all out ahead of time. I usually guess, because I usually have a pretty good instinct of which way it's going anyways. Okay? So example 4 says, explain how you would find the acceleration of each system. I'll set up the equation. What are the forces acting on mass 1? Get the obvious one. Normal force number 1. What else? Is there a rope? A rope, you say. Tension. Is there friction? Yeah, because there's a mu. Which way would friction be acting? I'll call that friction force number 1 to go with normal force number 1 and mass number 1. See how clever that is? Oh, and I didn't put a T on the there. What are the forces acting on mass 2? Get the obvious one. What else? There's an applied force to the right, tension to the left. Who's winning? I'm telling you it's not accelerating to the left because friction doesn't cause stuff to move. If it's accelerating at all, it's accelerating to the right. Oh, and if I crunch the numbers and I get a negative acceleration, all that tells me is friction's bigger than the applied. It's not accelerating at all. I find that the easiest way to go. Who's winning? So anything to the right is winner plus, anything to the left is loser minus. I walk along the rope. I run into a loser tension. I run into a winner tension. Oh, sorry. There's also a friction force number 2. Boy, that was the whole point of this. Thank you, Sophia. Oh, Sophia. Whoa, what killed myself. Candy for you. You know what? A Smartie, because that seems appropriate. There you go. Stab myself with my sword. Yeah. Oh, I broke my sword. I bet that happened too in the old days. So it would also, before I had done the plus tension, there should also have been a minus friction force number 2, and then a plus tension, and a minus friction force number 1. Is that everything? Double check carefully. Have I got everything along the rope? Check, check, check. You can cross stuff off as you go or put check marks or actually putting little dots underneath. Yeah.
Does that say right down that?
I don't know. I need more specific than that. Applied 1, applied, and then tension, and then friction number 2, and then tension, and then, can you figure it out? There you go. Yeah, I'm saying we can figure it out, right? Good, good, good. Good question. By the way, I will never make fun of you for asking to translate my writing. My writing is atrocious, and believe it or not, it improved. It used to be worse. That equals, have I looked at more than one mass for forces? Well, then it's going to be M1 plus M2 times A. And yes, once again, I could relax because tension would cancel. If I wanted to go further, I would say, okay, it's going to be F applied minus mu times normal force number 2 minus mu times normal force number 1. And then I would say, for normal force number 2, I don't know the normal force. Oh, but look. I know another force the same size as a normal force. What could I put in for normal force number 2? M2G. And then I could say, I don't know normal force number 1. Oh, but look. I know another force the same size as normal force number 1, M1G. And then I would probably, oh, hang on. You know what? My plus didn't come up. Sorry. I wrote a plus, it just didn't show up. That's M1 plus M2. The screen's starting to get a few dead spots. I hopefully get a new computer by next year. How would I get the A by itself? Yeah. Like I said, Isaac, I can't say this is tougher as much as it's longer. Okay? It would be very similar over here, except is there going to be any friction on M2? No. How much more am I doing here, Mr. Dewick? I'm almost done the lesson. I apologize, because I didn't want to give you guys homework over your Halloween weekend, but it just may happen because I went off too many story tangents. Okay. A, find the, oh, by the way, I like example A, I like example 5, I like example 5, example 5. You're going to have friction and more than one mass an awful lot on your test. Although probably I may just have it hanging over a cliff too, because there's drama. Hey, it's hanging over a cliff. What do they want me to find here? Fayez, what does part A want me to find? You know what I'm going to do first? Yeah, although technically, since I'm not going to redraw everything, I'm going to label my forces, but we'll call that a free body diagram, even though technically you're supposed to represent the mass with a dot and redraw it. So I know what you mean. Hey, good. Hey, folks, what are the forces acting on the 5 kilogram? I always start on the left. You don't have to, but so all our stuff looks the same. Let's do that. What are the forces acting on the 5 kilogram mass? Get the obvious one. Normal force number 1. Tension. Is there friction? Yeah, which way? And I'll call it friction force number 1. What are the forces acting on mass 2? Thank you for getting the obvious one. What else, Ty? I'll call it normal force number 2. I think it's the same size as gravity because there's no other vertical forces. What else? Ooh, there's an applied force to the right of 20, FAPP. What else? There's 2 forces to the left. Tension and friction force number 2. I'm losing you guys, and I've talked a lot, and there's 8 minutes left, and I want to give you a chance to practice a bit of this. So I'm going to assign the first part of the homework, which isn't going to have friction, and then we'll finish this off Monday. I'm also going to do a full lesson on Monday. My lesson on Monday is shorter. To probably record the homework. Right now, you should be able to handle number 1. What's mu? 0. Number 2? I know. Number 3? Number 4, number 5, number 6. You should be able to handle those. You don't have to get them all done for Monday. I do want you to have a fun Halloween, but if you know you're going to be busy next week in the evenings, you then might have to do some of this on the weekend to stay caught up. Definitely, folks, people are behind in the homework, and I understand last year, both in my class and in Mr. Kamozi's class, because he was away for the forces unit, people are wrestling with this. I'm deliberately slowing down and spending more time, but this is so fundamental. Try and get caught up, please.